Okay, before you start doing this exercise, you should have done two things. One is you should watch the video about um, instantaneous compounding that is given by a YouTuber. The other thing is you should do the investigation, the at-home investigation about instantaneous compounding. Okay, so if you've done those two things, go ahead and start the exercises. There's not really too much from the book reading here. It's mostly just the problem. So I'm just going to work a few problems here. Sketch on the set of axes the graphs of y equals 2 to the x, y equals e to the x, and y equals 3 to the x. Comment on any observations. Okay, so if we take any of these three, the first value is going to be the multiplier out front, which is 1 in every case, right? So 2 to the 0 is 1, e to the 0 is 1, and y 3 to the 0 is 1. So like all these graphs start out at the point 1, 0, comma 1. What about the second point? 1. So I'm going to use different colors for each one. So we'll use red for this one, and we'll use blue for this one, and we'll use purple for this one. Okay, so let's graph some points for 2 to the x. So the first point would be 1, the second point would be 2, the third point would be 4, the fourth the fourth point would be 8. 1, 2, 3, 4, 8. Okay, and then I'm going to graph the blue one. So 3 to the x, first point is 1, second point is 3, oops, the third point is 9, okay, and if I want, I'm going to connect these points, okay, so like blue, I'm going to connect like that, red, I'm going to connect like that. And now let's do e to the x. E to the x is a little bit tricky because it's not whole numbers. So it starts out at 1, or at 0, comma 1, and then 1, comma, now remember, e is like 2.71. So 2.7 to the 1 is 2.71. So it would be between the red and the blue value here, 2.71. And then the second value would be 2.71 squared, or you'll notice your calculator has an E button, if I can find it. Do you see it here? I don't see it. Oh, there it is. You go second e to the x. Oops, that's not what I want. Second e to the x. Okay, and then I put 2 because I want e squared. E squared is equal to 7.38. So 2 comma 7.38 is right there. Now you're starting to see a pattern here. Okay, now let's draw the graph of the heat. Okay, and then it says, so draw those three lines, and then it asks you, what is the relationship between the three? Is that what you would expect? Well, they're all very close together, right? What else is related among them? Which one's highest, which one's lowest? Well, 3 to the x is the highest, 2 to the x is the lowest, and e to the x is in between. Does that make sense? Yeah, because 2.71 is between 2 and 3. So if I put 2 to the x, 3 to the x, and 2.71 to the x, then I should expect the same behavior. I should expect that 2.71 to the x is kind of between 2 to the x and 3 to the x. Okay? So 2 to the x and 3 to the x are both exponential functions we're familiar with. E to the x is not really anything different than that. It's just between the two. Okay, so you can kind of see that in this graph. Okay. I'll skip that one. Okay. What about this one? Consider y equals 2 e to the x. Explain why y can never be less than 0. Well, why don't we try to make it 0 to start out with, okay? Well, what if we put 0 in for x? What do we get? Well, if you remember, if we put 0 in for an exponent, it'll always give you 1 for e to, like it would be e to the 0 would be 1. So y would be 2, okay? So 0 gives us 2. So 0 didn't work. You've been giving a negative number. What if I put a really big number? What if I put 100 in there? E to the 100, what would that be? It'd be a huge number. Okay, so 100 gives us a huge positive number. Okay, well, what if I put a really negative number then? I'm going to put like negative 100. So e to the negative 100. Well, that would just make, that would be 1 over e to the 100. So this would be a huge number on the bottom. It would be a fraction with those 1 on the top and a huge number on the bottom. It would be very close to 0, but not quite 0. Okay? And so it would just be, it would be like a really small number, but not 0. And then, so how can we even make it 0? Well, it turns out we can't. We can't, no matter what. No, if you put a real big number, it turns into a real big number. If you put a real small number, real negative number, you just get a really small number that's close to 0, but you never get there. And the reason why is because remember, there's a horizontal asymptote whenever you draw an exponential function, and the exponential function is approaching 0, but it never gets there. So not only does y never become less than 0, it never even becomes 0. So actually, y is always above 0, more than 0. Okay. Now, let's take one of these problems like this. Obviously, you're not going to do this without a calculator. How do we do it? Well, we just showed you that to do a exponent e, you do second log, and then you put any number here. So even if it's a fraction or a decimal, no problem, the calculator can figure it out. So that's about equal to 2.01. And that's 3 significant figures, you see. 1, 2, 3 significant figures. Do you know how to do significant figures? Significant figures is, if it's not a 0, then it's a significant figure. Any 0 that's between 2 significant figures is a significant figure. So this here is 3 significant figures. Okay, write the following as the power of e. I think the trickiest one is probably this one. So we'll do this one first, okay? So we'll have 1 over square root of e. Well, 1 over square root of e, square root of e is e to the 1/2, right? And now it's the inverse of e to the 1/2, so we could say e to the negative 1/2. And then we're just done, okay? We'll take this one here. Simplify that. Okay, so remember that if you have an exponent to an exponent, you may multiply these exponents together. So let's try to do that. 0.064 divided by 16 times t. You could use the calculator, but you could probably do this in your head too. 0.064 divided by 16 is 0.004. And I'm going to check that with the calculator because that's kind of a tricky one. 0.064 divided by 16. 0.004. Good. Okay, so I simplified it, and it's that 0.004 t. Find to 5 significant figures the values of these. And I'm not going to do these because it's just putting in your calculator and typing it in. Get a little practice doing that. Very easy. Let's see. On the same set of axes, sketch and draw clearly the graphs of, and they give me 3 functions here, all variations of e to the x. Let's see. First, we'll just do this one. Function, and remember that's just equal to f of x equals e to the x. So f of x equals e to the x. Remember that at 0 it's equal to 1, like all exponential functions. At 2 it's equal to, or at 0, at x equals 1 it's equal to 2.71, which is the approximate value of e. And remember that at 2, it's equal to about 8 point something. So we'll put it at 1, 2, 3, 4, 5, 6, 7, 8. It's about there. Okay? So e looks kind of like that. E to the x, sorry. What does e to the x minus 2 look like? Okay, with e to the x minus 2, if we put in 0, when x equals 0, it actually becomes e to the negative 2. Weird. Okay, so x equals 1, it's e to the negative 1. And x equals 0, or x equals 2, then it's equal to e to the 0. And then x equals 3, and then it's equal to e to the 1. So that's interesting. So like when I put e to the x minus 2, it takes on all the same values, but it takes them on shifted by 2, right? So I'm going to make this a different color. I'll make it green. So this one's green, and the green one is going to show that the exponent function is shifted over. It shifts over by 2 because I put e to the x minus 2. So this one is e to the x, and this one is e to the x minus 2. What does this do? E to the x plus 3. Well, e to the x plus 3, let's see, every time I put in let's put in x equals 0 for that one. When I put x equals 0 in here, instead of getting 1 out, I get 4 out, right? Because I get 1 plus 3. If I put x equals 1, instead of getting 2.71 out, I get 5.71. So let's graph some of those values. So for 0, I get 4. And for 1, I get 5.71. 4, 5.71. And then you can see that what I'm going to get is, I'm going to get the exponent function raised by 3. Okay? So when I do e to the x minus 2, it moves it over by 2. And when I do e to the x plus 3, it moves it up by 3. And now if you think back to when we did the investigation about exponentials, now you remember that we did a function that looks kind of like, we had like r to the x minus d times k plus c. We had something like that, right? And remember that when you add a c term, what it did was it moved it up and down. And when you put in the d term, it moved it left and right. And that's just what's happening here. The x minus 2 is moving it to the right by 2, and the plus 3 is moving it up by 3. So when you put in these modifying numbers, it just translates the exponent curve around the screen. Okay? All right, now we'll do one of these expanded and simplified. This is very similar to the other ones we've done. It's just instead of having a number here, you just have an e instead. We'll take this one. This is basically you just multiply this factor term to this, and then you multiply times that, so you get e to the x times e to the minus x minus 3 e to the x. E to the x times e to the minus x, that's just, you just add the exponents because they have the base in both, right? And that would just be the same as e to the 0, which is, of course, 1. And then you have minus 3 e to the x. So if you're going to simplify that, you would just say 1 minus 3 e to the x. I don't think you can simplify it any more than that. Okay? And shall we do one of these here? So e to the 1/2 x equals 1 over e squared. Can we solve that? So we got e to the 1/2 x. And what we're trying to do here is get the same base so that we can equate the exponents, right? 1 over e to the 2 is the same thing as e to the negative 2, right? Now that we have the same base, we can equate the exponents. So 1/2 x equals negative 2. And so now we multiply both sides by 2, and then we'll get x equals negative 4. So that's the answer. X equals negative 4. Okay. Shall we do this one, 14? The current flowing in the electrical circuit t seconds after it is switched off is given by I equals 75 times e to the negative 0.15t. What is the current still flowing in the circuit after 1 second, after 10 seconds? Okay, so this is just like the problems we did before where we put the equation in the calculator. The only tricky thing here maybe is that, you know, it doesn't have x's and y's in it. So you need to take the variables they gave and you need to translate to x and y. So instead of I, you're going to put y. And instead of t, you're going to put x. So it's 75 e to the negative 0.15t. Negative 0.15. Instead of t, you're going to put x, right? Oops, I just did something wrong here. I want 75 e to the 0.15x. And then I'll just delete these. Delete, 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 delete. And now I can graph it, see what it looks like. But what I really want to see is the table values. Because in the table values, it gives me the numbers that it's asking for. Now, you see it says after 1 second, after 10 seconds. My step size is way too big. I need to change the step size to 1. Okay, so now I can see that the initial value is 75, and after 1 second, it's 87.1, and after 10 seconds, it is 336. Okay. Use your graphics calculator to sketch two functions. One is I equals 75 e to the negative 0.15t, and the other is I equals 1. How do we sketch I equals 1? We just put here 1, okay? And then we're going to graph, and there's I equals 1. And now the other function, 75 e to the negative 0.15t, is just like way too high. We can't see it because we haven't, we're not making the window go up high enough. Let's make the window go up higher. We're going to make the y max equal 100. Then we'll see it. 100. Okay. Now we can see it. Okay. I think I need to put negative 0.15t. So I put second insert and I put a negative. I knew that was wrong because the graph was going up instead of down. Okay, now e to the negative 0.15t, I was expecting to see it go down, and now it's going down. And then I equals 1 is here. Hence, find how long it will take for the current to fall to 1 amp. Let's see, can you see that that's going down, but it's not near 1 yet? So how are we going to see that? Well, we're going to have to change the window size, and we're going to change the x max to something much bigger than 5. Let's say 200. Maybe that'll be enough to see it cross. Oh, there. It seems to have reached it. So we can use second table to see when it reaches the value I equals 1. It looks like we don't need to change the step size. Even with a step size of 1, we're going to get there pretty soon, right? 6, 5, 4, 3, 2, 1. There we go. So at between 28 and 29, it reaches I equals 1. So t equals 28 something. 28 or 29. Is it seconds? Probably? Yeah. All right. Now, if you wanted to find the exact value, there's a way to do that too. You can stop watching now if you're not interested, but basically when you have an intersection like that, and let's change the window size so we can see better. We'll change it to y max 50. It's still way too big. Let's change it to y max 'max, we'll put 10. And the x max, we could put something smaller like 50. Okay. And then what we're going to do is we're going to find out where the intersection is between these two graphs, and that'll tell us exactly where it is. So to find the intersection between these two curves, well, one's not a curve, one's a straight line, we're going to use second calc intersect. And then we say the first curve is the e function, yes it is. Second curve is y equals 1, yes it is. And then we say, what is your guess? And it doesn't matter because there's only one intersection. Your guess just needs to be close to it. So the intersection is 28.78, y equals 1. So do you see how the exact number would be around 28.8? And we had guessed between 28 and 29. So if we use the intersection function, we can find out that it is exactly, or more precisely, 28.8.